question
Le
aussi.
faire. Il suffit de mettre pin pour mon image et puis...
Et l'enregistrement vient de démarrer, puis tout le monde doit cliquer « J'ai compris » ou quitter la réunion. Là. Donc tout le monde est d'accord maintenant. Tout le monde qui reste est d'accord en principe.
André-Marie, est-ce que tu pourrais mettre quelqu'un co-host aussi en même temps pour qu'on puisse gérer les micros?
Oui, sauf que je ne sais pas comment faire ça.
Dans la fenêtre des participants, tu cliques sur les 3 petits points.
Je peux
Le
faire
plus.
Je peux faire mute all, mais... donc,
Mais dans la fenêtre participant, il y a un petit plus à droite, là, puis d'une personne, puis tu peux le mettre co-animateur ou co-animatrice.
Sélectionner la personne, oui. Okay.
Ça, c'est marqué more.
Oui, oui. OK. Donc, Olivier, ça va être ton problème.
Okay.
Donc, more chat. OK. C'est bon?
Parfait, oui.
Bonjour tout le monde. Donc aujourd'hui, le conférencier n'a pas vraiment besoin d'introduction. Il a été un pilier au département de physique à l'Université de Sherbrooke depuis presque 40 ans.
Plus que 40 ans.
Plus que 40 ans. Et il a fait de nombreuses contributions importantes, tant scientifiques comme administratives, et tout ça. Et donc, son intérêt de recherche se concentre surtout dans les superconducteurs à haute température, où il travaille depuis plus de 30 ans, peut-être 30 ans.
Oui.
Ouais. Et là aussi, il a fait des contributions très intéressantes. Aujourd'hui, il va partager un peu sa compréhension de ces matériaux avec nous. Donc, merci, André-Marie.
OK, merci beaucoup. Donc, oui, comme disait Yann, je suis assis, je vais parler en anglais. I'm really fascinated by high temperature superconductors. And there's a new twist that I will talk here about ultra quantum matter, which is another way to look at this problem. So if you have any question, you can interrupt. No, so the ultimate goal of this is to have a superconductor at room temperature. So you see, we are not really too far. These are different families of superconductors with the year they were discovered and the record they established at the time they were discovered. So in some cases, it's just because it's another family. And we see that you're close to the room temperature here with these materials, but at very, very high pressure. And these are understood in some sense, these materials. On ne voit pas l'écran partagé? Whoops, big problem.
Moi, je vois tout comme il faut, mais je ne te vois pas de toi.
Ah, mais ça, c'est correct. En principe, c'est Yann qui transmet mon image. OK? Mais vous voyez la présentation.
Oui.
OK. So, yeah, when we are in the other building, these things will be automatic and you won't have that many problems. So these are, despite the high transition temperature, they are believed to be in some sense conventional. So I will focus on these compounds that all have in common copper-oxygen planes. And so they look, one of them looks like this. So you have copper in black and oxygen in red. And you can think of the rest of the material as removing or adding electrons in the copper-oxygen planes. And then you can consider this two-dimensional model as sort of a caricature or the first-order model for all high-temperature superconductors that we call cuprates because they are copper-based. So the question is, who ordered this? Because they have a very complicated phase diagram. So at zero doping, so I will talk about doping, but here zero doping means 1 electron per unit cell, 1 valence electron per unit cell. Okay, it's an antiferromagnet in the ground state, and as you raise the temperature, it becomes paramagnetic, but it's still insulating. So we call it a Mott insulator. I will explain what a Mott insulator is in a little bit more detail. There's a phase that has where the density of state decreases. That's called pseudogap. Then there's this phase which has linear resistance, linear temperature dependence of resistance. It's called strange metal. It has some, perhaps some quantum critical point or phase transition here at zero temperature. And this superconductivity that is at high temperature is in the presence of strong repulsion. So I will show you why this is a problem and why it made these problems difficult. And it has competing ground states. You see there's a charge density, charge order here, spin density wave, and so on. So who ordered this is probably this guy, some kind of demon, but I have another hypothesis. That's the way that physicists who have looked at that problem for as long as me start to look like after a while. So the first thing we look at in the standard solid state books is the band structure. And here you see there's a single band that crosses the Fermi level. So it looks like a very simple problem. And it's believed that it can be described then by this model. That's a two-dimensional Hubbard model. So you have a lattice, a two-dimensional lattice, and there's hopping between sites. It's called T, and T prime for the second neighbor, and T double prime for third neighbor, etc. And if there are 2 electrons on the same atom, then there's a strong repulsion. It's called U. So the Hamiltonian looks like this. So if you have no interaction, U is 0, you just have these hopping terms, and then you get this band that I showed earlier. So plane waves are the solution for this problem. On the other hand, if I have only U, you see that the solution of the problem is to put, if you have, for example, a half filling, means 1 electron per unit cell. So you put 1 electron in each of these cells and they don't move. So on one hand, you have plane waves, and the other end, you have localized objects that look more like particles. So it's like the particle-wave duality, if you want. So localized basis is not a good basis, and the extended basis is not a good basis. And it turns out that the kinetic energy that's described by this is comparable to the potential energy. So the wave function is as complicated as you want. It's highly entangled if you want to use fashionable words. Okay, now I talked about ultra quantum. So 1 band and also spin a half. Spin a half is as far as you can imagine from classical spin, right? So suppose we are at half filling. So we have 1 electron per unit cell. And so it means that you have an electron here, an electron there. If U is dominating, you have no hopping. We start with no hopping. So that's a very simple solution. Now turn on the kinetic energy. Turn on T. What happens? Well, the electrons will want to jump, and they can, if the spins are anti-parallel. If they're parallel, Pauli does not allow you to make the jump. But if they are anti-parallel, they can. So it means that the wave function now, instead of being just this, will have admixtures of these terms, and they will be proportional to T over U, T being this hopping, because we're expanding around U, if you want. So as far as energy is concerned, the energy goes down with the quantity J here for just these 2 guys. And J is called the super exchange interaction. It's 4T squared over U. So that will play an important role in what follows. So I will ask you to remember a few things. You have to remember that there's this U for repulsion, that there's this T for hopping, and then there's J that's 4T squared over U. Now, for truth in advertising, this is not the correct model in the sense that there are oxygens here in between, and they play, we saw them as the red here in this plot, and they do play some role. So what I'm going to describe today is sort of work that's in a way relatively old. It's in the last 10 years or so. And what I will talk in part 2 is the role of oxygen, which turns out to be sort of a very nice, I don't know where to put very nice spectator that tells us a lot about what's going on. And I think you will be convinced in part 2 that we have sort of found something that is revealing as far as the mechanism of superconductivity is concerned. So let's see why we call this system a Mott insulator. You can see this with X-ray absorption. But first, let's talk about just theoretically. So a semiconductor here on the left, a semiconductor has a valence band and a conduction band. And if there are n atoms, okay, so each containing 2 energy levels, if you want, then there are 2 n states. And in a semiconductor, they're just separated by some gap. And now in a Mott insulator, then the interactions are very, very strong. So you have to imagine that U is very large. And we put at that filling one electron, I'm sorry, per unit cell. So what happens? So it takes a certain energy to remove electrons there. Now, if you put another electron on this, it has to go on an occupied site. So it costs an energy U. So it means that you have n states here that with energy that corresponds to removing electrons, and n state here to adding electrons. Now, what happens if you dope? If you dope a semiconductor, the Fermi level just moves. That's it. In a Mott system, it's very different. Why? Because now you have one less, you dope, so you have one less electron here, you dope with holes. So there are n-1 states here. So you can add electrons on that will cost energy U on n-1 states, and you can remove on n-1 state. And you have created 2 states, so you're left with 2 n states again. You have created 2 states near the Fermi level where you can put an electron up or down. So how do we see this experimentally? We take, like Patrick explained to me at some time, you take a very high energy photon that extracts an electron from a core state, and you look at the cross section, and then you will get, like, you see the energy here is 530 electron volts, so it's huge. And you start to be able to extract this core electron. So that's this first peak here. Now, suppose you dope, then this peak has to reduce in intensity. You see, if you dope, then the peak has gone down a little bit. And then this one here has gained intensity because you have states now that are available very near the Fermi level. So this is what happens as you dope. And you see that this one goes about twice as fast as the other one decreases. So it's quite convincing that this is a Mott insulator. What will be the take-home messages? So the take-home messages will be that most of the main features of the phase diagram follow from the Hubbard model, and that this physics is continuously connected to the Mott transition at that filling. So everything in the phase diagram is connected to the Mott transition. And we need to look beyond traditional tools of solid-state physics to be able to understand this. So I will tell you a little bit about the method and then about the one-band Hubbard model, its prediction for the phase diagram, for the pseudogap, for D-wave superconductivity. And I'll talk to you about the phase transition at the heart of the phase diagram. And part 2 will be on the 3-band Hubbard model, where oxygen can probe some of the details of the physics. So that's for some other time. So the way you work then is that you first use density functional theory to give you a basis. And then on this basis, you write down the Hubbard model and you solve it with dynamical mean field theory. So I will explain what dynamical mean field theory is. So it takes me, I timed it, it takes me 6 minutes. So if you lose track a little bit of what's going on, don't worry, because it's not crucial. But it's not standard solid state physics. So the problem that we have is to have at the same time the localized and the delocalized picture of the electron. So for the localized picture, suppose that you have an interaction U only on the 4 sides that are joined here on this square. Then if you want to look at the effect of interactions on the propagation of particles, you have to solve this problem of electrons in a bat. In other words, everything outside is not interacting, so it's called the Anderson model, and these electrons outside are non-interacting. So you can, all that they do is that they modify the way that the electrons propagate from site I here to site J. So it modifies the Green's function. So you can calculate the effect of interaction. That's called the self-energy. So you have to sum this series of diagrams to infinite order. Now look at the delocalized picture. Assume that you tile the infinite lattice with these squares. So if you tile the infinite lattice with these squares, you can still hop from one square to the other. So there's some energy K tilde. The Brillouin zone is now smaller because you have a bigger thing. And so the energy here will depend on this wave vector, but the self-energy here depends only on Ij on every site. So the way to solve this problem is to solve the same skeleton expansion with the Green's function Ij that is just projected back to the cluster. So there's the power of this is that there's a self-consistency relation now between the lattice and the solution to the localized problem. The self-energy is the same in both cases. So what you need to determine self-consistently is the way the electrons propagate in the bat. So it's called the hybridization to the bat. And this picture is called cellular dynamical mean field theory. There's also an equivalent with periodic boundary condition that I will not describe in detail. Now you need something to solve this localized problem. It's called an impurity solver. So one way to do it is with, like David Sénéchal does, is with exact diagonalization. And another way is to, there are many ways to use continuous time quantum Monte Carlo. One of them, if the interactions are strong, is to use a Monte Carlo procedure to compute to all orders in the hybridization function the observables. And now there are many softwares that are available to do that. We have our own. And there are many groups using these methods. I won't refer to everyone, but both in Europe, in the United States, and Japan. Now you need to critique this method. What is the problem with these methods, or what is the advantages and the disadvantages? Advantages, what about long-range order? Well, usually to do long-range order, you do some mean field somewhere. But here we never do mean field on the cluster. The mean field is done in the bat that's supposed to represent the infinite system. So it's determined self-consistently. So symmetry breaking is allowed only on the bat. There's no mean field factorization on the cluster. And what's included exactly is the short-range dynamical and spatial correlations. What's missing are the long wavelength particle-hole and particle-particle fluctuations. And it's good when the correlation lengths are small. So what to do, it's exact in the infinite size limit of the cluster, so you compare cluster of different sizes. And you can compare real space and momentum space clusters. Okay, back to our problem. You have any questions on the method? Okay, the phase diagram. I've already explained the antiferromagnetism when I explained to you the effect of J. Yes.
So this method is mainly for two-dimensional strongly correlated.
You can do it into any dimension you want. Actually,
Not like 3 dimensions too.
yes, yes, and it works best in infinite dimension where it's exact.
But these cluster sizes are bigger in 3 dimensions, so it's
Yeah,
harder to-
well, it's always a problem of computer power in the sense that even these small clusters, they are you remember, they are in an infinite bat.
Mm.
So it's still difficult to solve. And this bat is dynamical. I mean, it depends on frequency. That's what's important. This G0 is a function that depends on frequencies. You have a mean field that depends on frequencies. So I already explained the antiferromagnetism. Everybody's happy with that. Now it turns out that the full phase diagram, no, I just flipped the diagram. Now you can think of this axis now as electron filling instead of doping, and the vertical axis is still temperature. So the full diagram is this one. I had, sorry, Patrick, I had the reference and it disappeared. It's in a review paper with Patrick Fermi. So yeah, there are 2 sides to this diagram. So this is the so-called all dope side and the electron dope side. So that's the full phase diagram, and I will the electron dope side uses different methods, so that would be a completely other talk. And we work a lot on the electron dope cases, which is also very interesting. So this is a phase diagram that was found by the group of David Sénéchal, Alexandre and Foley and Simon Verret. You see that this is the order parameter. So what characterizes superconductivity and electron filling here on the horizontal axis. So this is half filling, 1 electron per unit cell. So you see the antiferromagnetic phase in red that has this the right asymmetric shape. And if you look at superconductivity, it follows the orange line. And then when it contacts antiferromagnetism, it goes down along this blue line. And similarly on the other side. So you see that it's not a bad start. Now I said that there are competing orders. So there are also charge and density waves and so on, and they are found in these large cluster calculations. But if we look at what we do locally, we still have this. So this is again order parameter as a function of doping this time. Superconductivity itself as a function of doping. And now if you look at the competing order bond density wave and pair density wave, these are the orange line is for pair density wave and the blue line is for bond density wave, and they compete with superconductivity. So superconductivity goes down. So you see that we have these systems as well. Oh my God. Okay, let me say a few words about the pseudogap. So this was done with Alexis Rimbaud, one of my students, and Maxime is now a faculty in Trois-Rivières. Patrick and Marion Ténon was in high school at that time. So the pseudogap, if you look at the spin susceptibility as a function of temperature, and you look in your textbook, you will see that it's supposed to be Pauli susceptibility, so it's independent of temperature. Here, there's clearly a loss of something, some spectral weight at the Fermi level. In standard textbook, it's just the density of states. Okay, so if you interpret it like that, there's a loss of density of states. Okay, and this loss of density states occurs along this red line that is slightly above another line where phase transitions occur. So this is what happens with DCA 12 sites, and you can see that it has the same shape as the experiment. If you look in detail, the doping does not quite correspond. I mean, this is electron filling and hole doping, but this is again an effect of the 3-band model. I mean, the point is that you have the same behavior with a maximum here, and then at large doping, it goes like that. So 6 sites gives the same, with 4 sites gives the same. So what is the physical origin? think of a singlet. Okay, again, it's very quantum mechanical quantity. Singlet. If you take, for example, a simple four-side cluster that I talked about earlier, then the most probable state, not the only one, but the most probable state is a linear combination of these pairs of singlets. So it's close to what Anderson called the resonating valence bond model. So that's the origin of the pseudogap. And we can compare with some experiments that Louis' group did, where there is temperature and doping again for one compound, YBCO, and for another compound. And this T star is not for the spin susceptibility, it's for the resistivity, but the spin susceptibility just starts a little bit earlier. And this is what we get. So as a function of U, you see that U equals 9 is this black curve. If you go to U equals 36 is this red curve. So it goes down when you increase U. And here you see that it goes down also when the Néel temperature goes down. So it means that, again, it's related to J. So when you increase U, J decreases. So that's why this goes down. And if J is involved, it means these singlets are coming in. So that's okay.
So does the T star in different materials agree with that scaling with J? So if you look at YBCO, you compare it to LSCO, the T star are not exactly the same.
No, but so that's yeah. So that's what we saw. That's what we saw here, right? So you can look at other ones. I have not looked systematically at all the other ones. I will skip this part. We don't have that much time. So D-wave superconductivity. Okay, let's talk about ordinary superconductivity. So where does superconductivity comes in these the first materials, just simple mercury or lead or simple metals. So if an electron comes in and scatters off a phonon, okay, the phonon is very slow. So you can have an electron with momentum minus p that scatters off the same phonon. And basically what you have created are pairs. So we have pairs of electrons that go into another pair of electrons that are both characterized by p and minus p. And you see that the effect is retarded. You know? You cannot put two electrons at the same place at the same time, but you can put them at different times. So the equation, it's retarded. So in superconductivity, there are two ingredients. There are these Cooper pairs that I just mentioned, and there's also phase coherence. So let's see how phase coherence comes in. This is the pair wave function for the incoming electrons, and this is the pair wave function for the outgoing electrons. And that's the interaction U. Now do some mean field. Okay, we can do some mean field there. So this is only the potential energy part of the interaction. But you see, we can lower the energy if this U is attractive, like for phonons, you know, a positive charge and negative charge. So if U is attractive, you can lower the energy. And the condition is that the phase of these complex objects is the same independently of P and P prime. Okay, if the phase is random here, it will average out to 0. But if the phase is the same, it will lower the energy. So that's the mechanism between for superconductivity. And to get something that's non-zero here, what you need to do is to have a wave function that is a linear combination of wave functions with different number of particles, because this destroys two particles. So you need to have different numbers of particles, but you have to add them up with the same phase. And if you're familiar with coherent states with photons, it's the same idea. Okay, now in these superconductors, we don't have, the phase is not completely independent of P and P prime. I call them D-wave superconductors. So what does that mean? It means that the order parameter, if you look in one direction, it has a certain sign. And if you flip by 90 degrees, it's the same value, but it changes sign. So why is this helpful with repulsive forces like we saw for antiferromagnetism? Suppose this is repulsive, so it's positive. How can we get a lowering of energy? We can get that if P minus P prime scatters, for example, from the X to the Y axis. And if when it's large, let's say it's large for this type of scattering, and if psi changes sign going from the X to the Y axis, you've gained the minus sign you needed. Okay, so that's a simple way of seeing why in the presence of very strong repulsive forces, you have D wave. The other advantage of D wave is that it vanishes when it's on the same side, right? So if you have strong repulsion, that's what you expect. So it's consistent with the BCS equation. I won't go into that, but basically you're replacing the phonon with this antiferromagnetic spin wave. And that was proposed a long time ago, actually, by our colleague Bourbonnais with Emery and Béal-Monod. And if you look at these calculations with these dynamical mean field calculations, this is what is plotted here is 1 over the pair susceptibility. The pair susceptibility diverges at the transition. So if 1 over P goes to 0, you have a transition. And they looked at very different cluster sizes, and the blow up here shows that for large cluster sizes, it goes to 0 before T equals 0. So there's a transition, but that's U equals 4. In our case, if you do experiments, you see that the antiferromagnetic correlation length is small, actually. But so you're in a regime where the interactions, it's J that's important. So now if I rewrite the spin operators in terms of fermions, you see that you can factor 2 C's, and you can do some mean field there. C. And then if you define the D wave order parameter that changes sign if you go from X to Y, then you find that at the mean field level, you do have some attraction in the D wave channel. But if you start from the original Hubbard model with U, and you try to factor the U there, you never get D wave superconductivity, you just get antiferromagnetism. So that has been the challenge of the field, if you want. This cartoon at strong coupling sort of gives an indication that it might be possible. But we need to do more serious calculations, and this is what we have done. So this is a plot of the superconducting transition temperature for the group of Gould and Millis with 8 sites. So there is a transition temperature, and if you increase the number of sites in the back, you see again something that looks more like the experiments here. And what we find here for different values of U is this. So forget this part for now. So it starts at U equals 7. So the superconducting transition temperature is this here. The color is just the value of the order parameter. So this is a temperature on this axis and doping on that axis. Few things are remarkable. One is that if you go here from 7 to U equals 16, you see that it goes down if you increase U. So again, it suggests that J is very important because J is proportional to 1 over U. Okay, the other thing is that it is skewed a little bit too much towards half filling compared with these larger cluster size calculations. But if we take into account phase fluctuations, in other words, you look at the spin, at the what's called the stiffness of the order parameter, you can, and you include that effect, you see that it becomes more symmetrical. So this can be interpreted as a mean field transition temperature. Yes, Gennady.
Yeah, I have a question. These models, when they do these dynamic mean field, do they have either like what kind of focus they have inside the cluster, like T, the prime?
Oh yeah, inside the cluster, for this model that I showed here, that I'm showing here, there's only T upping, and here they have a T prime. Okay, and here they don't.
And the next aspect, so is it like T prime which changes?
No, it's only U that changes here.
U.
Only
So
U.
they have the same set of.
T prime is equal to 0, T is equal to 0. They have the same set of T and T prime. So there are many experiments that suggest that C Cooper pairs above the superconducting transition temperature. So that suggests an explanation, actually. As I told you, in this region, very close to F filling, there are a lot of phase fluctuations. I said that the superconductor is phase coherent, but if you go to the superconducting transition temperature, it's called the Kostelis-Taubes mechanism. You can be in a regime where the pairs are formed, but they are not coherent because the phase fluctuates. Okay. Now this phase diagram, everything here is about the normal state, except for this line here that is the superconducting transition temperature. You see that it goes to 0 at F filling because it's a Mott insulator. And at large doping, then it's 0 because there's not enough anti-ferromagnetic correlations. Now this line is the pseudogap line that I talked about earlier that falls very quickly like we saw in the plot. And then there are these other lines here. The background color is just the value of the scattering rate. And these are other observable quantities. But I want to show, okay, then I'm just reminding you of these other calculations. Now, what we computed is the condensation energy. So in the ground state, why is it superconducting? And what we see here in this region at large doping, the red shows potential energy, the difference between the potential energy in the superconducting and in the normal state. So the superconducting state has a lower potential energy in this case. So that's a simple explanation I gave at the beginning. Very close to F filling, that's actually, it's kinetic energy that you gain. So the blue is kinetic energy. And you see that there's a change at this place here that's related to the pseudogap and to many other phenomena in the normal state. And this can be observed using some rules in optical experiments. They have seen this change from potential to kinetic energy. Okay, now let's vary the value of U. This is the plot I was just showing you, U equals 7. At U equals 9, you see that the kinetic energy gain goes over a broader scale. And what's surprising here is that as you decrease the value of U, you see a phase transition sticking out here. So we can understand these things that seem to come from nowhere as in the reality coming from a phase transition that's at a temperature too low for us to compute. So I hope you ask questions for this, but I skip the glue. And I will end with a phase transition at the heart of the phase diagram and its relation to the Mott transition. So this is the work of Giovanni Sordi at the Royal Holloway in London and Auli at Rutgers and my former student Patrick Simon. So when we looked at the Hubbard model, there was a side that was with the delocalized electron. So this metallic side. And then there's a U. So when U dominates, we expect insulator. So at half filling, there is indeed a change from metal to insulator. And it occurs through a phase transition. It's not a crossover. At 0 temperature, it's a phase transition. And then as you increase the temperature, you go to a critical point. And above the critical point, there's this so-called Widom line that's known in the field of statistical physics. So if you're here, something strange happened, look down. It may be because there was a first order transition somewhere below with a critical point. So now let's dope. Okay, so this was at filling. Let's see what happens when we dope and see if there's a relation to everything we found before. So what you see, this is chemical potential here on this axis and filling on this axis. So you see that as I change the chemical potential here, I stick to 1. Why is that? It's because the chemical potential is in the gap. So in the gap, you change it, it doesn't change the filling. And then it crosses over to some metallic state. It's compressible. dN, d mu is different from 0. And then there's a first order transition. That's the first order transition I showed you before. So if we get rid of the superconductivity and just look at the normal state in this region where we saw the first order transition, there's a Widom line here. And there's a precursor to this Widom line that is the maximum in the spin susceptibility. That's the T star that we saw before. So we explained both the T star in the spin susceptibility in the pseudogap, and also inside the superconducting state, why is there this change from potential energy driven to kinetic energy driven? And it's all related to the existence of this phase transition. It's not there in one dimension. So the phi and Sénéchal verified this. So that's the Widom line I talked about. This I call the Sordi transition, and this is the T star here on this. Now I want to show you, well, first, there's an objection to this. The objection is that here, if we don't allow antiferromagnetism in the bat, we find that. But if we allow the bat to become antiferromagnetic if it wants, if it's self-consistent, it will become antiferromagnetic. So perhaps all this is an artifact of this antiferromagnetism. So to get rid of this argument, or to answer this argument, we look at the anisotropic, well, in general, the anisotropic triangular lattice. And if T prime here, this upping is equal to T, we are in a triangular lattice. We need to stretch this a little bit, but it's a triangular lattice. And on the triangular lattice, we get spiral order at 0 temperature, but it takes a while before you get there. And in fact, there are many phase diagrams that show that you don't get spiral, you get chiral spin liquids or whatever. But the point is that at finite temperature, antiferromagnetism will not be in the way. So what happens? These are the results of Pierre-Olivier Downey doing his thesis, and Charles David also, and Olivier, who's now at New York, and Maxime in Trois-Rivières. So if you look here, you see the curve is similar. Now it's distorted because we don't have particle-hole symmetry. So you see here, you get a metal, and here you get a pseudo gap. Actually in this whole region, you get a pseudo gap in the sense that if you look at the density of states as a function of frequency, that's what is plotted here. Density of states as a function of frequency. You see there's not a real gap, but there's a loss in density of states. At that filling here in the orange point, you get a real gap. It's hard to see here, but it really goes at a real gap. And then again, a pseudo gap in this region and a metallic state there. Okay, this is a complicated plot, but the only thing I want to say is that this is at a fixed temperature. So again, this is a fixed temperature, and what is plotted here is a phase diagram of U and chemical potential. So there's a chemical potential here where you are at half filling. And this is the chemical potential where you're at half filling. And you can see the Mott transition. So there's U, and there's you stick to half filling, and you see that you go to the insulating state that is there.
The chemical potential, the unit of the chemical potential is T.
It's T. Everything I should have said, it all measured in your units of little t.
And so 4T is
8T is the width.
the width.
Yes, and in this case it's 9T. Yes.
Okay, good.
So because it's triangular lattice. So you see the Mott transition at that filling is this. You go from metal to insulator. The colors are just the compressibility. And then if you go to finite filling, there's this Sordi transition. And you see that it's continuously connected to the Mott transition. And it turns out that it has some universal properties. You change the value of U, and if you just shift the chemical potential, the curves all fit on one another until there's a transition. So it's I mean, it's suggestive of something. We don't know why. We can use a fashionable word there. So, yeah, let me summarize. Yes.
Just a question before the transition. When you go through the transition, what transition? Are they all like metal insulated transitions or?
Okay, good question. So the mud transition is metal insulator. The Sordi transition is metal-metal, except one metal has a pseudo gap and the other one does not. Okay.
Metal gap will stay when you finish.
Yes, both are gapless. Yes. So you see here, if you're in this region here, you get a metal, and in this region, you have this pseudo gap, and there's a first order transition in between. So at fixed chemical potential, you have two densities that are possible. So the transition is first order, but it's metal-metal. Yeah.
So basically what it means is that there's like T star above that transition. So there's already a precursor of the Sordi transition
Yes.
above that up to T star.
Yes.
And then you got this signature of the pseudo gap, even though it's not yet fully open, and then there's a transition. That's what.
Okay. The question was, yeah,
So
is this plot here?
Oh, yeah. So you start from high temperature.
So you start from high temperature. You see there's the maximum in the spin susceptibility occurs along this purple line. And then if you keep decreasing, there's something that happens to the spin susceptibility. Again, it changes curvature, it turns out. It was going down, and now it is going to zero, but with a different curvature.
Okay.
So this is what happens along the Widom line here. And so if you're far from this first order transition, the only thing you see is a crossover to the pseudo gap state that is living here. And if you start here, you see you would get to the first order transition. And if you start just a little bit next to it, there's nothing. And if you go back to, we have to go back forever. So if you go back to these experiments, you see that there's the T star line ends very abruptly. Okay. So it's similar to what we find here. So let me summarize. So intrinsic to the dope mud insulator, there's a pseudo gap. There's a first order transition as a function of doping if there is no competing order. And it's that if the first order transition has a critical point at sufficiently low temperature, it may look like a quantum critical point. The quantum critical point is a transition at zero temperature. Then there's D-wave superconductivity within the presence of short-range spin fluctuations. So we have a tendency to form singlets, and that leads to superconductivity. There are other effects that we have looked at. So for example, the effect of near neighbor repulsion. So even if the near neighbor repulsion V is much larger than J, you still get superconductivity. The V is screened by the Hubbard interaction. And there are other recent experiments that are consistent with the dope mud pictures. And there's a whole talk that could be done on entanglement-related properties and not the broken symmetry phase characterize the onset of the pseudo gap at finite temperature. And there's a staff of Mammoth that was very helpful. And thank you.
Question?
Yes, Sid.
So it seems that both T star and TC still be like the maximum value of T star.
Est-ce qu'il sera possible de répéter
Oui,
les
oui, je vais
questions?
la répéter quand ça va être fini. Oui.
Yeah, so I was wondering like what makes pseudogap and superconductivity to be different if they're both mediated by J somehow, because you showed that the pseudogap also involves singlets on the cluster, and superconductivity is also mediated by singlet fluctuations on the cluster.
So the question is, if J explains both the pseudogap and the superconductivity, why do you have two different phenomena instead of just one? So I would answer that the pseudogap is sort of a high temperature phenomenon where you see that J just causes some crossover with a tendency to form singlets. And then if the temperature is sufficiently low, then you long range order. But the pseudogap is not only, it ends before superconductivity. As a function of doping, the pseudogap ends before the superconductivity ends. So the pseudogap is a very strong coupling effect related to the formation of J. But superconductivity can exist both at strong coupling when J is important. And I showed you that on the other side of the transition, you get a potential energy gain, which is really the weak coupling mechanism for superconductivity. So you have the superconductivity is in some sense more robust to this. It can exist both at weak and at strong coupling. So yes, the question is whether pseudogap is a sort of a precursor of strong coupling superconductivity. So I would answer yes.
Michel? Microphone, Michel.
Thank you for the nice presentations. I have two questions. So you seem to relate the superconductivity to J, and J depends on T over U. So as you decrease U, would you expect TC to increase?
Yes, it does. It does, yes.
But you showed some graph when U was not large enough, then there would be no TC.
No, it decreases. So that the maximum TC occurs right at the crossover, if you want, between weak coupling, where U is smaller than the weak correlation, I should say, where U is smaller than the bandwidth, and strong coupling, where U is larger than the bandwidth. So the maximum superconductivity you can get is in this intermediate regime. And when I talk about this, when I talk about the 3-band model for part 2, you will see that as well. Yes, you can see even in this plot, for example, you can see that the maximum here occurs at U equals 7.
Mm-hmm.
And then if you go, for example, to U equals 5.6 here, now there's no mud gap. So at half filling, you're in a metallic state if you don't allow for antiferromagnetism. So you see, it doesn't go to 0 anymore. It's actually maximum at half filling. Again, if you artificially forbid antiferromagnetism. But if you focus just on the superconductivity, you see that from weak to strong coupling, it first increases and then it starts to decrease.
Another question is that does this model agrees with the pressure dependence of TC?
Yes, yeah. The question is whether it agrees with the pressure dependence of TC, and the answer is yes, because if you apply pressure on the whole dope cuprates, then the TC increases. So it means that applying pressure means increasing the hopping between unit cells, which means that T goes up, and if T goes up, J goes up. Okay, so it's consistent. Now it turns out that in electron doped cuprates, it's the opposite. But that can also be understood by the same argument, because as I will show some other time, not in part 2, but perhaps part 3 or part 17, I don't know. It's like, if it works out, you do a sequel. So for now, there's only part 2 that's in the predicted. So if you see, if you're at weak coupling here, if you increase the hopping T, it's like decreasing U, so you go this way. Because this way, if you decrease U, the superconductivity goes down. Yes.
Okay.
But it's very simple-minded picture. It's not based on actual calculations of the hopping and everything.
You assume that U doesn't change with pressure.
Yeah, I assume that U doesn't change with pressure.
And maybe one last thing that I think in your Sauty phase, Sauty transitions, what's the order parameter?
In the what? I'm sorry, I missed the question.
You you said you had a Sauty phase transition.
Sauty transition, yes.
What's the order parameter that is represent that phase?
Yes, very good question. So let's start with this. So what is the order parameter here at that filling for the mud transition? Well, an example is the double occupancy, for example. So there's a jump in double occupancy as you go from there to there. So double occupancy, double occupancy, I mean the expectation value of N up times N down. So you don't expect that the expectation value of N up and down has anything to do with an order parameter, but here it does actually. So it's like a liquid gas transition in some sense. It has a scalar order parameter, and this critical point is in the Ising universality class. So in the case of the Sordi transition, it's the density that jumps from here to there. So you can take the density as the order parameter. In the same way as in a liquid gas transition, you take the density as the order parameter. So it's again in the Ising universality class, it has the same, it has a first order transition, a critical point, and the exponents are those.
But it's not going from 0 to some finite value, it just change.
Yeah, the same way as in liquid gas transition. It's the difference in density that is 0 at the critical point, and that increases as you go down along the first order line. You see what I mean? So you can take the difference in density as the order parameter if you want it to be really 0 at the critical point.
And do you have a symmetry breaking something? Usually phase transitions relate to some symmetry that it's broken? Or?
Well, it's the same as in the liquid gas transition. So in the liquid gas transition, what is the broken symmetry? If you map that to an Ising model, you can see an order parameter in terms of the magnetization. So here it's the same idea. If you map this to an Ising model, you can make the magnetization becomes the order parameter, or here the difference in density is the order parameter. But strictly speaking, there's no broken symmetry. I mean, a liquid and a gas have the same symmetry.
Because they're both gapless, as you said, you can't have like analogy quantization, it has to be gap state, right? If you're going between different two gapless states, you can't have like sort of Eisen or whatever.
I'm sorry, can you repeat? I will repeat for the.
Well, I'm saying that if you have a transition between two gapless states.
Yeah, if I have a transition between two gapless states, yes.
It's hard to expect that there is a order parameter sort of Eisen or whatever class because it's a gapless state. It's quantum critical, so it's basically zeros. Conventional order must be 0 on both sides.
I suppose, yeah, if you talk about a quantum critical point, you mean that this point goes all the way to 0 temperature, right? So in our case, it goes to very, very low temperature, but it's not 0 temperature. So at 0 temperature, at least as far as we can extrapolate in this first order transition here or this one here, it still remains exactly first order at 0 temperature. So we don't get into this paradox that at the quantum critical point you don't have an order parameter. It's really, you have to think of liquid gas transition at finite temperature. That's what's happening here. And there's a critical point in the liquid gas transition. So it's the same thing for the mud transition. And for the Sordi transition, I did not plot it the same way, but that's exactly the same thing.
Okay, we have a question from Bertrand.
Yes, thank you, André-Marie. That was very, very nice talk. On this slide precisely, I have a question. So the Widom line, as far as I know, is some kind of a thermodynamic line, which is seen experimentally as a peak in the heat capacity, for example.
Yes, absolutely. Yes, yes.
And I was wondering how you go from this to the linear dependence of resistivity that is observed in cuprates.
Okay, so if you ask any theorist to compute a transport quantity, he will run away. So, okay, but nevertheless, we are doing it within some approximations that are less controlled than for thermodynamic quantities. And it turns out that if you are, well, it's another paper. If you, so there's this pseudo gap here, but if you start from the zero temperature and you see you don't touch this pseudo gap line. You're just here at optimal, let's say, if superconductivity, people call it optimal doping. Let's go back to this picture. So you have superconductivity. Okay, the dome will become more symmetrical when you take into account phase fluctuations, and then the pseudo gap ends here at this point. And this is where at zero temperature, there's this change from potential to kinetic energy driven. And if you include the effect of phase fluctuation, that's about, okay, I need to do some plots here. We just have some preliminary results there, but the optimal TC occurs basically where this pseudo gap line ends. So if you start from optimal to TC, you don't have a pseudo gap in the way. So that would be the strange metal. And when we do calculations of resistivity in this region here and going down, here we see a pseudo gap. In other words, there is a direction in momentum space where the scattering rate becomes very large, and there's another direction where the scattering rate is linear in temperature. And when you're on this side, then all the directions have linear in temperature scattering rate. But so in some sense, it's related to the existence of this transition in the sense that it's to the right of this transition, but not more than that.
Okay, so there is nothing really fundamental with the fact that the resistance is linear with temperature.
Okay,
it's a certain cut in the phase diagram.
Well, what is fundamental about the linear resistance, as far as I'm concerned, is that you have these spin fluctuations that are in some sense responsible in the end of the whole phase diagram. Okay, so if the spin fluctuations become soft at this in this region, so their characteristic energy is small, then you go in a regime where the it's like the high temperature regime of phonons. If you remember phonons, if you're above the Debye temperature, the resistivity is linear. And it's because why? Because the Bose factor tells you that the number of phonons is proportional to kBT. That's it. And you don't have any characteristic energy anymore because the Debye temperature is small. So here, similarly, the spin fluctuations are doing the whole phase diagram. And if they become soft near the phase transition, then it means that if you compute the resistivity, it will be linear again for the same reason as the phonons. It's because you're above the characteristic spin fluctuation frequency. And then the number of spin waves are bosons. So the number of spin waves is proportional to kBT. And that gives you the scattering rate that's linear in temperature.
Okay, thank you.
Maybe one last question from Denis.
Thank you very much. Very nice talk. I'm a novice in this topic, so maybe pardon my kind of naive question, but I would like to understand kind of the physical, high order physical picture of the Widom line, and in particular, I have kind of an interest in an interest in the following sense. So obviously. Superconducting state is formed by correlations, and you've made that point loud and clear. So I'm curious if you look at statistical fluctuations of the spin degree of freedom, particular not in the superconducting state, but near this Widom line. Would there be any precursors of the superconducting state that would appear in the maybe higher order statistical moments? The way I interpret this plot is, in some sense, these lines that you plot is kind of first order analysis of the probably ultimately related to the spin fluctuations. But is there any information beyond this first order, second, and higher, particularly near this Widom line?
Did everybody understand the question? Okay, so this is a very interesting question. Let me first mention that, okay, if you go back to this, okay. So the first part of your question, you were talking about the maximum in specific heat, right, in the Widom line. And indeed, there's some divergence at the critical point, so you expect that there's still some maximum left as you go away. And indeed, within these methods, if we compute the specific heat, we do see a maximum across the Widom line. But I should go back to this. Okay, along this Widom line, we see a maximum in specific heat, and that's also observed experimentally by the group of Louis. There's some maximum in specific heat. Now, the second part of your question is whether there's information into higher order moment of the spin fluctuations. So, okay, that will be part 15 of my talk. So if we look here, basically, this is what this paper addresses, but by computing the entanglement entropy across the Widom line. And what you find is that the entanglement related properties do see the existence of this Widom line. And entanglement entropy contains information about all correlations, not only the first or second, all correlations. The problem with this calculation is that it's still very primitive because it considers the entanglement between entropy between one site and the rest of the lattice. You would want to do as a function of system size if you want, but at least if you look at the way that one site is entangled with the rest of the lattice, we do see signatures of this in the entanglement related properties. In that case, it's not a maximum. I think it's more like an inflection point, but there is some, that's the best answer I can give at this point. And if you're interested in looking at higher moments, there's good reasons. Yeah, perhaps one could do that. Yeah. Does that answer the question?
Yes, excellent. Thank you so much. Maybe just a quick follow-up. So would you know if there are any experimental groups that are looking to verify or to explore the statistics beyond the first moment, so to say?
The statistic beyond the first moment in the spin fluctuation. But
yeah, exactly.
If Bertrand Relais is still there, he can perhaps answer. Yeah. Can you answer, Bertrand?
Yeah, I would. Well, what I know are experiments on higher moments, but on electrical properties, so current or voltage. I know there are there have been some experiments on magnetization fluctuations, but I guess here it would be more complicated. There is no net magnetization or whatsoever. But I mean, if there is a, let's say, higher order spin correlations, would that translate into some statistical properties of current fluctuations?
I would imagine.
Another thing I can say is that one thing that has been measured is the Fisher information for spin fluctuations, because the Fisher information is, I'm not sure I'm saying this correctly. Sorry, getting tired, I suppose, but this this Fisher information is related to actually spin-spin fluctuations that are measured in neutron scattering experiments. So that part has been done, but again, a little bit like entanglement properties, it looks at I guess in that case, it's only another way to look at spin-spin fluctuations and not at higher moments of the spin fluctuations. Yes.
Okay.
So in this paper, we also looked at mutual information.
Well, thank you so much. I'll be sure to read your paper. Thank you very much.
Okay, so let's
Okay. So thank you for coming. Thank you.
Merci beaucoup.
Okay. I hope you all show up for part 2. Even more interesting.
Next week.
No, it will be probably in January. We already have everyone for this term. I just exchanged place with Ian, actually.
And who knows, might be somewhere more interesting than here.
Yes.
You have to repeat the part 1.
No, you see, very little.
C'était extraordinairement clair.
Ok, merci.
C'est très bien.
Merci.
Au revoir, merci beaucoup.
Merci, bye bye.
Thank you.
Okay, thank you. Je vais arrêter l'enregistrement ici.
Peut-être, puisqu'on Chloé est là, puis André-Marie,
Oui.
j'ai cru comprendre que dorénavant, c'est peut-être Chloé qui va s'occuper du partager le lien Zoom. Je ne sais pas, André-Marie, es-tu d'accord avec toi, ça t'arrangerait aussi?
Oui, mais il n'y a rien qui empêche qu'on enregistre tous les deux. Là, je veux dire,
Non, pour les...
là, j'ai enregistré juste parce qu'il y a des gens ici qui m'ont demandé de l'enregistrer. Je savais
Oui.
pas.